take black holes. Carl Schwarzschild saw the possibility for black holes within the framework of general relativity back in 1916. John Michell, using Newtonian physics, hypothesized their existence even earlier, all the way back in 1783. But that means that for 55 years using relativity, or 188 years using Newtonian physics, we'd known about the theoretical possibility of black holes, but never actually saw any. The first black hole, Cygnus X1, was only spotted for certain in 1971. If it happened once, it's no stretch to believe it could be happening again. In the vast sea of scientific possibilities and outlandish ideas, exotic stars and strange forms of matter perhaps exist that are predicted, prolific, but are currently unperceived. What are these objects? Who knows? That's just it. They're unproven. But I and scientists around the world have a few ideas. I'm Alex McColgan and you're watching Astrum. And in today's Supercut, we'll be looking at some of the strangest objects or states of the universe that could be real, if only we could find one to know for sure. Be sure to check back in after the next 188 years to see how many did turn out to exist. This video may not age well. Unsurprisingly, for astronomers, one of the first things we'll turn our gaze towards are stars. Stars are some of the most beautiful and awe-inspiring objects in the universe. Through violent thermonuclear reactions, they emit enormous amounts of light, illuminating the night sky and heating up any nearby planets in the process. Through mergers and powerful explosions, stars are also responsible for producing the heavy elements that make up much of the matter we see around us. Astronomers and astrophysicists have come a long way toward understanding how stars operate, to the point where we can even predict how long it will be before our sun runs out of fuel and transforms into a red giant. But today, we're not just going to talk about the types of stars we're familiar with. Instead, we're going to contemplate stars we've never seen before, ones that astrophysicists say could hypothetically exist, including ones that are quite literally made of vacuum. First, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas or plasma and not solid matter, you couldn't stand on its surface like you would on the Earth. The Sun's gravity would pull you down toward the center. So why doesn't the gas at the surface get pulled inwards too? It turns out that there is a pressure pushing outward from the Sun's core that counterbalances this pull of gravity. The main source of this pressure is the radiation created by fusion reactions in the core, the same radiation responsible for carrying light and heat from the Sun to the Earth. Whether you think of radiation as individual photons or waves in the electromagnetic field, its path from the core towards the outer layers of the Sun will cause an outward push in all directions. This radiation pressure wouldn't be enough to stop you from falling into the Sun, but it's just enough to stop the Sun's own gas, which is relatively light, from collapsing in on itself. This balancing act between inward pulling gravity and outward pushing pressure is a feature of pretty much all known types of stars. What differentiates different types of stars is where that pressure comes from. For our Sun, the pressure comes from fusing hydrogen into helium. When the Sun runs out of hydrogen in about 5 billion years, it will become a red giant star and begin to generate its pressure by fusing helium into even heavier nuclei like carbon and oxygen. Eventually, the Sun will also run out of helium and any other light elements that could be used for fuel for nuclear fusion. At that point, it will collapse into a small star known as a white dwarf. Since no more fusion is occurring anymore, white dwarfs are sometimes called stellar remnants instead of stars. But if there's no more fusion, where does the pressure to support these stellar remnants come from? It turns out that gravity pulls the gas of a white dwarf inward until it's so dense that a new type of pressure emerges, known as electron degeneracy pressure. This is a purely quantum mechanical effect, and it's the same effect that's responsible for you not being able to pass your hand through solid objects. Electrons simply cannot get too close to each other without an extraordinary amount of energy. But some stellar remnants are so massive that even electron degeneracy pressure isn't strong enough to counteract the pull of gravity. This is called the Chandrasekhar limit. It's absolutely impossible to have a stable white dwarf any heavier than 1.4 times the mass of the Sun. If a star has burned through all its nuclear fuel and its core is still heavier than the Chandrasekhar limit, that core will collapse in on itself until it becomes so dense that an even stronger type of quantum pressure emerges, known as neutron degeneracy pressure, which, as you may have guessed, prevents neutrons from getting too close to each other. A star that reaches this state is called a neutron star, the smallest and densest known class of stellar objects. So now you might be wondering, is there a maximum mass that a neutron star can have while still being supported by neutron degeneracy pressure? And there is. This time it's about 2.2 times the mass of the Sun. Any heavier than that, and the neutron star would keep collapsing under the influence of its own gravity until, well, actually, not until anything. As far as we know, neutron degeneracy pressure is the strongest possible pressure that ordinary matter can exert, so there's nothing left to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the fate that might await some of the most massive stars we've observed in the universe. From the perspective of an outside observer, these stars would get so dense that all we'd be able to see is a black hole. That's a lot of pressure. Now, you might feel like you resonate with that, but if so, perhaps it's time to start finding yourself a new career, something a little more laid back and fun. You might want to try software developing. And yes, training for that can be surprisingly fun thanks to the sponsor of today's video, Boot.dev. Boot.dev is no ordinary coding course. Their website feels more like you're playing a fantasy adventure with quests and gamified elements that make each interactive task feel whimsical and entertaining. But by the end of it, you'll have coded entire projects, making it a great way to gain real-life experience and skills. If you get stuck, there's a great community who can help, or you can talk to the AI bear. Yes, there is one of those, and he's surprisingly good at code. The first few chapters with all the interactive activities are free to trial. Even after the free demo, everything on their website is completely free to read. So go check it out for yourself by scanning my QR code or clicking this link in the description below. If you use my code ASTROM, you can get 25% off your first payment for Boot.dev. But then, scientists started to wonder, what would happen to a star that wasn't made of ordinary matter? If exotic forms of matter could hypothetically produce even larger pressures than neutron degeneracy pressure, then what new kinds of stars could exist? You might think that we could just continue the pattern that we were starting to see earlier. Stars could get even smaller and even denser than neutron stars, as long as they were supported by some even greater pressure. You might think that the only limit on how small these stars would get would be the point of no return, where they would turn into black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Instead, physicist Hans Adolf Buchdahl showed in 1959 that a star made of any realistic form of matter with positive energy density and pressure can't be smaller the 9/8 times its Schwarzschild radius. It might not sound like a big difference, but that factor of 9/8 means that any realistic star has to be noticeably larger than a black hole, making it much easier to tell them apart. That's when physicists began asking about stars that Buchdahl would call less realistic. For example, what if a star was made of matter that allows for pressure to be negative in some regions and positive in others? Then Buchdahl's limit wouldn't apply, and that star would be less than 9/8 times its Schwarzschild radius. In fact, it could be arbitrarily close to the size of a black hole with the same mass. As a side note, theoretical stars like these that could mimic the appearance of black holes came to be quite a nuisance for astrophysicists, since now every time they discovered something that they thought was a black hole, they couldn't just say they discovered a black hole. They had to qualify that it's either a black hole or an extremely compact object mimicking a black hole, even though in their hearts most of them are quite convinced that it's a black hole. But back to the main point. What would these exotic stars with negative pressures even look like? The answer turns out to be even weirder than you might have guessed. Tolman, Oppenheimer, and Volkov derived an equation in the 1930s that describes how the pressure of a stable star changes as you go outward from its center. These days, it's just called the TOV equation for short. If the center of a star has a significantly negative pressure, which would exert some sort of attractive pull instead of a push, the TOV equation says that this star can only be stable and in balance with its own gravity if its pressure does something really wonky. First, the pressure has to blow up to negative infinity somewhere in the star. Then it has to flip sign to positive infinity and decrease outwards from there until it reaches zero pressure, marking the star's outer surface. The exact location of the infinite pressure depends on what the pressure is at the center. So if you tune that central pressure just right, you can keep the pressure finite right up until the edge of the star. That happens when the pressure at the center is exactly equal and opposite to the star's energy density there. In this special case, the TOV equations say that the pressure and energy density remain constant, equal, and opposite throughout the entire volume of the star right up until its surface. If you've seen some of our other episodes, this might ring a bell or two. A constant positive energy density paired with a constant but negative pressure. That doesn't sound like any star we've seen before, but it's starting to sound more like a mysterious component of our universe: dark energy. And since the pressure and energy density in a gravastar are equal in magnitude, it's not just any kind of dark energy. Those are the exact properties of vacuum energy. That's why this special exotic star came to be known as a gravitational vacuum star, or gravastar for short. Inside of a gravastar, there is precisely zero gravitational force, because the positive energy and negative pressure respectively exert a gravitational pull and push that cancel each other out. And since the pressure in gravastars is constant, there is no pressure gradient to exert any sort of push in one direction or another either. This means that if you found yourself inside of a gravastar, you would neither be pulled in nor pushed out. You could float freely, just as though you were in a real vacuum. Another curious feature of stars with negative pressures is that the closer you get to the special limit of a gravastar, which, if you recall, is when the infinite pressure surface gets pushed out to the edge of the star, the more their size approaches that of a black hole with the same mass. This raises two key questions that have recently gotten a lot of attention from physicists. First, how can we tell whether the extremely compact objects astronomers have observed in merger events and at the center of large galaxies are black holes or just exotic stars with nearly the same size? And second, if gravastars are real and scattered throughout the entire universe, could they be the dark energy that's been making the universe accelerate for the past 5 billion years? To answer the first question, physicists rely on the main distinction between black holes and other compact objects, the existence of an event horizon. You see, the defining feature of a black hole is that nothing that falls inside or even touches the surface of a black hole can ever come back out. On the other hand, if an exotic star is even slightly larger than its Schwarzschild radius, it would not have an event horizon, and it would potentially be able to emit information outwards in the form of light. Not only that, but objects without event horizons could have different signatures in their gravitational wave emissions than those of a black hole's during a merger. This would allow us to tell them apart by measuring and analyzing those gravitational waves using observatories like LIGO. But even with this battery of tests, it turns out sufficiently small and dense stars can still be difficult to distinguish from black holes. So far, the best we can do is to say that the radius of the black hole candidates we see in the universe is at least approximately equal to their Schwarzschild radius. In some cases, that's just a rough estimate, but in others, we've calculated that radius to within 40 decimal places. As for the second question about dark energy, that's where things get really heated. In early 2023, an analysis led by physicists at the University of Hawaii found that astronomical observations of massive black holes showed them to be growing in mass over time at exactly the same rate that dark energy would be expected to grow over time due to the expansion of the universe. They came to the inevitable conclusion that black holes must be made of dark energy, and that they are really more like gravastars than ordinary black holes with infinite density singularities at their centers. This conclusion was fiercely contested. Astronomers came out arguing that the analysis of the observational data wasn't quite right, and theoretical physicists came out arguing that the expansion of the universe should have nothing to do with the growth of black holes in any case. So while the idea that dark energy could exist in the form of gravastars sounds exciting, it looks like the scientific community isn't going to be convinced unless it's simultaneously supported by better data and more compelling theoretical models. So while gravastars may exist, we are far from proving them. And they might look too much like black holes to be able to easily spot in the first place. But the next exotic object I'll explore today should be as recognizably distinct from a black hole as it's possible to get. They are black holes' opposite, the push to a black hole's pull. They are white holes, and there's no reason in physics why they couldn't exist. I want to start off with a simple analogy. If I ask you to imagine a cone, you'll probably think of either something that points up, like a traffic cone, or something that points down, like an ice cream cone. These are what we think of as cones in the real world. But if you write down the most general mathematical equation for a cone and try graphing it, you'll get something that looks like two cones glued together. You see, a mathematical cone has two halves, one that points up and one that points down, connected at their tips. And what we think of as cones in the real world are actually just chopped up pieces of the full mathematical cone. Black holes are exactly the same way. Let me explain. Many of the black holes we see in the universe are remnants of massive stars, whose extreme gravity caused them to collapse in on themselves. Once a black hole is created, it becomes permanently separated from the world around it by a spherical barrier known as the event horizon. Anything can fall into the black hole, but nothing, not even light, can come out. This structure of space-time can be neatly summarized in what physicists call a Penrose diagram, which is a way of representing an infinite space-time in a finite drawing. The key feature of a Penrose diagram is that light travels upwards at 45-degree angles, making it easy to distinguish regions where light can or cannot enter. In this diagram, Region 1 is the regular universe, containing the original star before it turned into a black hole, and everything outside it, from the infinite past to the infinite future. Region 2 is the black hole, and is separated from the rest of the universe by its event horizon. You can see how it's easy for light to enter the black hole, Region 2, but it's impossible for light to exit. It will inevitably hit the singularity instead. The same holds true for ordinary matter, which moves slower than light, and so in this diagram can only travel upwards at angles steeper than 45 degrees. So what's so special about this Penrose diagram is that it accounts for the formation of the black hole at some specific point in time, when the star collapsed in on itself. In the far past, there was no event horizon or black hole to speak of, and light could travel freely across all of space. But while this diagram represents the kind of black hole we're used to seeing in the real world, it's only one piece of the full mathematical description of black holes in general relativity. In other words, it is the lone ice cream cone of black hole diagrams. So, what happens if we forget the real world and imagine an ideal black hole with an infinite past, leaving behind the baggage of collapsing stars and everything else in the physical universe? What is the black hole analog of the full mathematical cone? It might look like a simple extension of our original Penrose diagram, but this diagram comes with physics that's a little upside down. Region 1 is still our regular universe, and Region 2 is still a black hole with an inevitable singularity in its future. But the maths also describes something that looks like the inverse of a black hole in Region 3. Instead of a singularity in its future, Region 3 has a singularity in its past. And if you draw the motion of light rays at 45-degree angles, you see that it's straightforward for light to leave Region 3, but it can never enter it. This type of region is exactly what we would call a white hole. It's the space-time analog of a traffic cone. But that's not all. If you look beyond the white hole, you'll see there's a patch of space-time labeled Region 4, with the same connections to the black and white holes in the middle of the regular universe. This patch is a parallel universe, and it's entirely disconnected from the universe in Region 1, since it's impossible for even light to travel from one region to the other. The upshot of all this is that the same mathematical equation describing the regular universe and the black hole also describes the parallel universe and the white hole. This doesn't mean that every black hole comes attached to a white hole though. Just like with cones, the real universe can contain chopped up pieces of the full mathematical solution. But this does mean that even if white holes are less common than their black hole counterparts, or even if there aren't any white holes connected to our universe at all, it doesn't make them any less scientific, in the sense that they are equally consistent with the laws of physics. In our analogy, if you imagine that ice cream cones remain extremely popular, while traffic cones become difficult to produce and are phased out of existence, that doesn't make the idea of a traffic cone any less real. This is more or less the status of white holes today. The notion of a white hole makes perfect sense, but it's possible that any white holes that existed in the past were unstable and were similarly phased out of existence. If you're wondering whether there could be some more stable white holes that have just escaped our sight, you're not the only one. And you should stick around for when we talk about the tiniest possible white holes in just a few minutes. But first, buckle up, because the Penrose diagram can describe more than just white holes. We are about to go to a whole new level of warped space-time, into the realm of wormholes and parallel universes. The no-hair theorem says that a black hole can have up to 3 intrinsic properties: mass, charge, and spin. But the Penrose diagram I showed you only described the simplest kind of black hole, which was electrically neutral and completely stationary. The diagrams for charged or spinning black holes are much more complicated, but they're also much more exciting because they completely alter our understanding of singularities, and they give rise to new and fascinating regions of space-time. Let's have a look at the Penrose diagram for a spinning black hole as an example. Instead of 4 distinct regions of space-time, there are now 8 types of regions that repeat themselves in an infinite pattern of universes. Region 1 through 4 are the same ones we saw before. These are the regular universe, the black hole, the white hole, and the parallel universe. But now that the black hole is spinning, its geometry no longer has an unavoidable singularity in its future, and the white hole similarly loses the singularity that existed in its past. So what actually happens after you cross the event horizon of a spinning black hole? At first, you'll be drawn towards the center of the black hole just like you'd expect. But eventually, you'll cross a threshold known as the inner horizon, beyond which the geometry of space-time unwarps and lets you stop yourself from falling even deeper. In these innermost regions, marked 5 and 7, you can float freely towards or away from the center of the black hole. You could even touch the singularity if you wanted to, though I wouldn't recommend it. Here in these innermost regions of a curved, rotating space-time, you are officially in a wormhole. And if it weren't for the fact that you are permanently separated from everyone who stayed in Region 1, this would have been the perfect time for you to brag about your wild space adventures. At this point, you're also faced with a bit of a fork in the road. One option is to keep moving inward and go around the singularity, which takes the shape of a ring instead of a point for spinning black holes. This path would take you to regions 6 or 8 in the diagram. But it's quite possible that the existence of this path is actually a flaw in the predictions of general relativity, rather than a true description of reality. Because going even in a single loop around the singularity can lead to causal paradoxes where you visit your own past. A safer bet would be to turn around and move outwards, crossing back into the inner horizon that you just came out of. This would take you into region 3, a white hole, which would then carry you all the way out to a brand new universe, similar to the structure to the one you started out in originally, but sadly without your friends or family waiting for you. In fact, by the time you get here, your old universe will have already experienced an infinite amount of time. You would be living in a whole new definition of the future. Okay, let's step back into reality. As fun as that journey through the wormhole was in theory, you probably couldn't survive it in practice. And honestly, there's a good chance that the wormhole itself would collapse once you disturbed its space-time. So, how much of this mathematical structure can we expect to see in the real world? Spinning black holes with event horizons appear to be everywhere in the universe, but what goes on inside of them is still largely unknown. There are 2 main reasons for why physics inside real black holes might be different from what the Penrose diagram would lead you to believe. First, when black holes form from the turbulent collapse of massive stars, some assumptions that went into making the Penrose diagram are violated, like that the black hole existed forever, or that the universe around it is perfectly symmetric and doesn't contain random infalling humans. And second, the theory of general relativity used to construct the Penrose diagram might itself only be approximately correct, breaking down near the singularity where the curvature gets most extreme. So there's a good chance that some predictions of the diagram, especially the most problematic ones involving singularities and time travel paradoxes, aren't real features of a highly curved space-time. But the existence of white holes is more of an open possibility, leaving plenty of room for speculation about how they might come to be and whether they might leave any observational footprints for us to discover. One hypothesis that's recently gained some traction is that a white hole is born whenever a black hole dies. And no, this isn't some magical story of reincarnation or voodoo. It's a genuine attempt to understand the full life cycle of black holes with at least some level of mathematical backing. You see, even an isolated black hole in an otherwise empty space will continuously emit particles known as Hawking radiation, causing it to gradually shrink and lose mass over time. But once the black hole reaches the super tiny Planck mass, just about 20 micrograms, we have no way of predicting what future awaits it, at least not without a full theory of quantum gravity. This is where loop quantum gravity comes in, a proposed link between gravity and quantum mechanics, in which space itself is made of discrete loops. In short, the equations of loop quantum gravity predict that instead of continuing to shrink even smaller than the Planck mass, such a tiny black hole is instead more likely to quantum tunnel into a white hole, spewing out its contents back into the universe over an extended period of time. Incredibly, even though this white hole will be similarly small and light, it can contain an enormous amount of entropy, because its interior geometry will have been stretched into a thin tube with an extremely large volume. This store of entropy could potentially open a pathway for any information that falls into a black hole to be recovered in the distant future, solving a decades-long problem in theoretical physics known as the information paradox. As the white hole releases this information, it begins to slowly fade out of existence, the space-time around it loses its curvature, and its life cycle comes to a close. In general relativity, our whole universe is predicted to have had a singularity in its past, namely 14 billion years ago at the moment of the Big Bang. In this way, the universe is like an uncharged, stationary white hole. But if loop quantum gravity says that white holes can be born when black holes collapse, could the same be true about the creation of our universe? Could it be that our expanding universe was born from the ashes of an older, contracting space-time? As crazy as this seems, loop quantum gravity says that may well be the case. So, perhaps white holes as a concept are not so far-fetched. Maybe it's time to start believing in white holes, because, in a way, maybe we are in one. So, white holes certainly could exist in the real world, even if we haven't definitively nailed one down yet via observation. But I've glossed over another part of the Penrose diagram that might have made you raise an eyebrow. The Penrose diagram I used had no issue referencing parallel universes. But that's a big claim. Could entire universes, inaccessible to ours, yet running alongside us, just out of reach, actually exist? There's some logical reasons to believe so. But before we get to that, we need to turn our gaze to a more baffling cosmic mystery, and the worst prediction in physics ever made. It starts with a deceptively simple question. Why is our universe expanding? One of the first things you might learn in a physics class is that gravity is an attractive force between two objects, whose strength is proportional to each of their masses. Gravity keeps planets locked in orbit around the Sun. It keeps stars grouped together in the Milky Way, and it even attracts galaxies together to form galaxy clusters and superclusters. But if we zoom out further, this gravitational attraction begins to act in reverse, causing galaxy clusters to accelerate away from each other rather than drawing each other in. So, what's going on here? Einstein's theory of general relativity gives us a lens through which we can understand this strange behavior. In general relativity, space isn't just some background in which other things can move around. Instead, space itself can stretch and warp and evolve over time. Einstein showed that in this framework, gravity is no longer a force, but rather a distortion of an object's inertial path in a dynamical spacetime. For example, when a planet orbits around the Sun, in Einstein's description, it's merely following a straight line path in a curved space. This means what we observe as a repulsive force between galaxy clusters should really be thought of as an accelerated stretching of the space between them. But what could possibly cause the expansion of space to accelerate like this on the largest scales of the universe? To begin to answer this question, we need to know what causes space-time to stretch and warp to begin with. In Newton's theory of gravity, all objects with mass exerted a gravitational pull. And in general relativity, all objects with mass curve the space-time around them. But Einstein showed that in addition to mass, any form of energy or pressure will also influence the dynamics of space-time. Energy density is how much energy is found within a given volume, how much pop, heat, zap, and motion exists within a given space, and in our universe has always been found to be positive. Pressure is how much force over an area the contents of that space sends pushing into the rest of the universe around it. Think interstellar dust pushing on each other whenever they bump into each other in the void. As you can imagine, for objects so far apart, this pressure value hovers a little over 0 on a cosmic scale. When these values are cumulatively positive, as in the following formula, their influence on the space around them causes the space around them to contract in. Essentially, they create gravity by decelerating the stretching of space. However, conceivably, if you were somehow to set the values of this equation so that pressure was negative and greater than the positive energy density, that minus sign would cause the whole thing to flip, and you would accelerate the stretching of space. In effect, you would end up with a volume of space filled with a kind of anti-gravity, a dark energy. It's a little nebulous, as it's tricky to visualize anything with a truly negative pressure. How can you have less than 0 atoms in a patch of space, after all? But atoms are not the only thing that exerts pressure. After all, pressure is simply a force applied across an area. Fields can also apply forces. Think a magnetic field, dragging a piece of iron in towards a bar magnet, or 2 magnets pushing each other away. If dark energy was some kind of field that pushed away not just other magnets, but everything, then this would match what we see the universe doing. Vacuum itself having dark energy and enough of it to slowly, very gently push the universe apart. Scientists have thought a lot about dark energy over the years and have even figured out what its combined energy density and pressure needed to be to create the rate of spatial expansion that we witness. It's around 10 to the power minus 9 in SI units, which is a very small number, which is why we don't notice it here on Earth, and only spot it on the grand cosmological scale of the universe. This is actually good news, because it turns out that if the number was much higher or lower than this, things would get very bad for our chance of existing. Let me show you what I mean, with a quick sketch of the history of the universe. Here is the full history of the universe from the moment just after the Big Bang to the present. This is the dark energy density measured by astronomers. Scientists believe its negative pressure has kept this density roughly constant for billions of years. And although there is new evidence coming to light that shows dark energy may be weakening over time, for our purposes, we can just keep the value consistent. It doesn't change the point we're making, as you'll see in a moment. This is the density of ordinary matter in the universe, which has little to no pressure. The density decreases over time because the expansion of the universe dilutes the matter within it. Finally, this is the density of radiation in the universe, including photons and other extremely light particles. The positive pressure of radiation makes it dilute away even more quickly than ordinary matter. Towards the beginning of time, for a very short period, there were no atoms. Very quickly though, protons and neutrons fused together to create the first atomic nuclei in the very early universe.